maximize the number of people. So in my team by 6 people, so there's going to be what I call. But this problem, when you define in the graph theory, this is the maximum independent set in a given graph and has no polynomial contribution. So what can we do to solve this impossible problem? We can take all possible solutions. We can go for the heuristic. We can try approximate solution. Or we can divide the problem and then conquer the solution. Let's go into more detail into divide and conquer approach. What we are going to do is to divide the infinity and solve each part separately and recursively. And then construct a solution of the whole problem based on the solution of the two parts. And given a graph, we divide it into and then we recursively divide. And the graph decomposition tells you how to divide the graph. So given a graph, we divide and then we recursively divide. And apart from only dividing the graph decomposition itself also is more. As you know, many hard problems are polynomials and probable in space. Decomposition can be used to tell us how a structure, how close it exists to a tree, or how it distinguishes from a tree. And computation methods of the decomposition tree in such a way lead to different big parameters. There are several big parameters based on the decomposition tree. So, 3-week, 5-week, 6-week, 1-week, and given a decomposition tree, there are 6 parameters attribute algorithms for the numerical decomposition. So one such parameter is union. Now let's look which properties of the decomposition tree led to the definition or led to the initiation of Bergen. So given a graph, you have a decomposition, like you have a bifurcation of the vertex, different partition of the vertices, and the two independent sets in this graph has a red neighborhood in this side. If you rename this base as a path in the decomposition, so this green independent set has this red neighborhood in this side. And the purple independent set in this side also has this red neighborhood in this side. Any independent set in this A bar side or on the other side, excluding this vertices from the independent set can be marked with either the blue independent set or the purple independent set. And from the complexity of this set, there is no difference between these two sets. So this leads to the notion of equivalence, the neighborhood equivalence. So the complete sets are neighborhood equivalent if their neighborhood on the other side is equal. And we can compute the number of different unions of neighborhoods that can subtract for the ABCD decomposition tree. And this measures the complexity or quantifies the Bergen decomposition. Let's have a detailed look at the Bergen decomposition tree. So given a graph, and it starts out with all the vertices in the root of the decomposition tree. Actually corresponds to the bipartite graph, where the edges in the bipartite graph is this edges crossing the path. And the big functions of the decomposition, we have the quartic structures to rearrange it, and the bigger the decomposition, we result maximum wealth of this function, and the width of the graph will be minimum width to the all possible decomposition. So now let's see how this function is computed. We call it unions of neighborhoods. So given a quartic structure, we want to compute all the different unions of neighborhoods that they can produce on the other side. So we might take none of the vertices, and then if you take A, it has no neighborhood on the other side. B, it has these two neighbors. Union of AB, we have two neighborhoods. C, and the fixed factor actually over these parameters representing this in the order of the length of the loop, not the subsets of into the all subsets of this loop. So to compare easily with other parameters, it is correspondingly to take the logarithm ratio of the number of the unions of neighborhoods as per this function, and this is for the Boolean dimension. So far we have seen that how Boolean dimensions and Boolean matrices become. And there are so many other parameters. So how this parameter Boolean base compares with them. So it's just simply this plus 1. Boolean is equal to less than 80. And Boolean is equal to 1 plus 1 is square plus 1 6. And there are different graph classes. We are dealing with better bounds than other parameters, like a simple graph, grid graph, bounding graph, where other parameters have over options, meaning they have less features. And our main goal was to solve hard problems using decomposition phase. So let's see how hard problems looks like in parameters by using this parameter. So theory, again we try to solve the maximum indeterminacy problem. It's true to the theory, so for free space and Boolean which is true to the Boolean. And the similarly again for Boolean matrices. So we have seen the theoretical values and how they look like in different graph classes and its algorithms. So now it's time for the practical aspects and how these things look like or is this approach feasible for applying in practice. So its parameters algorithm using graph decomposition has mainly two stages, like finding a good decomposition and then solving the problem using this decomposition. So we focus on the first step, so finding a good decomposition. So what do we mean by good decomposition? The efficiency of the bounding problem depends on the width of the decomposition. And good decomposition can increase the efficiency of the all the exit algorithms using this decomposition. So if we spend time on finding decomposition of small bits, we can use this decomposition to solve indeterminacy problem, dimension, etc. So we have matrix, dimension, and so we go for heuristic. So here is our computation. We try heuristics to find different Boolean decomposition and test with their efficiency or performance. So what we do? We generate greedy Boolean decomposition and then try to improve it by research. We have counted maximum indeterminacy and partial evaluation of the Boolean dimension of the good function. We tried complete cross reference. We tried generating Boolean decomposition and tree decomposition. We also tested exact and random Boolean decomposition. We have tried caterpillar decomposition. dynamic programming using Arduino calculation. So now I will highlight all the approaches in this and show you some experimental results. So generating greedy Boolean decomposition. So this was our first approach, and this has two main stages. So greedily generate an initializing decomposition tree, then try to include the tree in the local code. So what we do in greedy initialization, we create an ordering that the choices are greedy at each stage, and the selection function is based on the Boolean dimension. Like having a vertex, we will choose that vertex which moves to the ordering will give you the least Boolean dimension over all the vertices. And then in this way, after having an initial decomposition tree, we tried local search to see if the Boolean bit of the decomposition can be included. And it was done trying random swapping between seedlings in the decomposition tree. And if better cut found, then we keep the cut and then try to include the seedling. So having this approach, we two vertices having these edges swapping the cut. This has Boolean dimension. And if we swap this vertex C and D, then this has Boolean dimension. It's not here, it's 4, it's 2. So this we tried in siblings and try to find better. So this approach was tested experimentally. We tested comparing 500 plus confused libraries, because our goal was to check how this Boolean bit upper bound from this decomposition compared with this upper bound. And then we tested on graphs having vertices less than 300 vertices. And the edge density of the graphs were ranging from 1% to 85%. And the ratio of speculative upper bound and Boolean upper bound locally was minimum 1.15 to maximum 2.1. And average equal 2.15. And this is graphical representation of the ratio in upper bound to Boolean upper bound. This is plotted against age density. And it can be seen that with increased age density, the ratio has a little tendency to increase. Leading to the more accurate computing more graphs of higher density. And let's look how local search includes the Boolean bit of the initial decomposition tree. So this is a graph of 51 vertices where 8 was concentric. We found an initial decomposition of 1, and then it rapidly improved via local search and came to a little more than 6 within almost 5 to 6 seconds. And then it took quite long, around 100 seconds, to get a little improvement. And then we stopped at somehow. Let's look at another graph of the reactive with local search. This is a graph with 128 vertices and 5,000 edges. And for this graph, the 5.5, it keeps on improving in almost every direction. So there was not constantly improving in all the edges. And this might be due to the random process or due to the graph structure. So this was our first approach, and working with this approach we actually get aware of the roadblocks or the challenges that we might face generating the Boolean decomposition. And later on, the Boolean bit upper bound achieved through this approach was compared with the rank bit upper bound using a similar approach like Bergen and Bergen. And they tested on the graphs from previously, and the graphs were having between 25 and 256 vertices. observe that the number of different unions of neighborhoods is same as the number of maximum independences in the bipartite graph for the class. So then what we do? We try counting maximum independences for the partial evaluation of the class. So we actually went through the well-known algorithms for counting maximal peaks in the literature because they are quite well known, and we did the dual of these algorithms, and they are quite well used in practice. Like the Bronc-Harwood one, this is a recursive backtracking approach for listing all maximal peaks, and there is one tomita, which is a bit important, but the basic structure is same as the Bronc-Harwood approach. And there was a counting of maximum independences algorithm by Gaspers from 2008. It uses some reduction rules, and quite new one was fixed from explained. And there is a figure and survey. This was also for maximal peak, and we tested the dual of this one. So we implemented the previous algorithms and then ended up devising our own counting algorithm. So how our algorithm look like? The basic structure is the same as recursive backtracking approach. Given two vertices P and X, it will count all the maximum independences, including some vertices from P, but no vertices from X. But we have to dominate the vertex with X somehow. And then select the vertex from P, and then count all the maximum independences, including the vertex P and excluding the vertex P. So the summation of these two will be the maximum independences in P. And how our algorithm differs from the previous algorithm? This is, in this case, let's select the vertex blank line. So the difference lies in how we select the vertex. And one of thing we do is connected comparison. Let's say we take a vertex in our algorithm. So what our different versions of our algorithm is, like this nested dissection is definitely indicates connected component, and nested dissection is just ordering. So this will just follow the nested dissection ordering, and this next definitely will in each stage select the maximum degree vertex and check for connected component. And the sorting separator is together with the nested dissection ordering to sort each separators locally in the nested dissection ordering. And this nested dissection plus sort adjacency list is following the nested dissection ordering and sorting the adjacency list of each vertex and the maximum degree vertex in the maximum number of vertex that it has in each separator with constant. And one is a combination of sorting the separator and also sorting the adjacency list. So first we compare, first let me give you the dataset that we used for this experiment. We use graphs from previous library, and this will be the graph that we will be using the computation of Boolean dimensions. We also use graphs from Florida's sparse matrix collection. We use grid graphs because they were hard to separate, and bipartite graphs. And the X density was ranging from 1% to 100%, and the number of maximum independences ranging from 2 to 10 to the 20. And the graph partition after method, that this was the one that we used to generate the nested dissection ordering. So first we compare the algorithm of Tomita and Gaspers algorithm. And for Gaspers algorithm, we try different variations. So G100 is using the size reduction rules at each pulse. And G50 is using the reduction rules in 50% pulse. And G0 is not using the reduction rules, it's only the recursive backtracking. And now also we have the algorithm by Tomita, which is the number of days, then we actually find a big difference in time between these two things. And also we tested the same approach and plotted against the average degree, and you can see that when the average degree is around from 2 to 5, this is there is a big difference between these two molecules of the quantum mechanics. And this again is quite expensive. And the next laboratory has I have mentioned that it prefers memory. Its memory requirement is also exponential in the low dimension, whereas the memory requirement of the quantum algorithm is. We decided to use the counting maximum independence for the rest of our algorithms for evaluation. And then we try some simple pre-processing rules. The instruction has the vertex at degree 0, then we remove the vertex at degree 1 vertex and 3. Because if we remove this vertex, the of the reduced graph, we can always revert the reduction rules and get the original graph. And we tested this one experimentally and graphs from probabilistic network. And the minimum vertex reduction was 0%, maximum was 48%, with an average of 20%. And for the same set of graph with few pre-processing rules, the average vertex reduction was 50%. And for this graph, the minimum vertex reduction was 20% and maximum was 96% and the average was 47%. Then we tried another approach to generate Boolean decomposition from 3D decomposition. And it's not from Boolean decomposition, but regressive decomposition of primitive. We can generate the Boolean decomposition of primitive. So what we do, we actually take a graph and generate a 3D decomposition using the minimum degree heuristic, finding the elimination, ordering, and triangulation, and then find the 3D decomposition. And given the 3D decomposition, we do several steps to transform the 3D decomposition to Boolean decomposition. So let me see, by giving a graph, we get a 3D decomposition. Let's do 3D decomposition. This vertex, if we think it this is 3, this vertex 3, this can appear here and here as well with 2 terms, 2 children. But in Boolean decomposition, the root partitions the vertices into different vertex subsets. So what we do, first we actually remove multiple copies of any vertex from the decomposition tree, and we retain only the topmost copy of every vertex. And in Boolean decomposition, every vertex should be mapped to a leaf of the decomposition tree, so we copy the vertices that are not in the leaf to a leaf. And next, every vertex in the leaf should also be in its parent in the Boolean decomposition tree. So we copy the vertices that are not in parent, we copy those vertices. And now the only thing left is to make the graph a full binary one. And then like where we have more than 2 children, then we substitute the binary graph. And from the 3D decomposition, we get the Boolean decomposition. And this approach were also tested experimentally, and we actually consider 2 measures. The quality of the decomposition tree we measure in 2 ways: the Boolean upper bound of the decomposition tree and the time needed to generate and evaluate the decomposition tree. So in terms of we study the average ratio of qubit upper bound to the Boolean upper bound from this assay was 2.8. And for the same set of graph, using the first factor, PD plus local first factor, then we have turned out to be almost 1/3. And these are different random graphs with varying H probability. This is n equals 30, 40, and 50. And if you vary the H density, the random graph, the random Boolean decomposition is evenly varied in this way. We must also take exact and random Boolean decomposition of random graphs. And then we tried a different kind of decomposition that we name capital decomposition. Because sometimes it's easier to work with simple decomposition, where internal nodes of the decomposition is a part, not a string, and as it's part decomposition and also tree decomposition. So given a graph, the decomposition will look like this. And the vertex, we can think of it as the vertex ordering. And the width of the decomposition will be maximum width of the bipartite graph. And you can think of that here is a bipartite graph, here is a bipartite graph. And the number of maximum independent sets, maximum in any of these bipartite graphs will give you the upper bound of the capital decomposition. So to evaluate this decomposition, we try different vertex ordering. Taking the vertex, we have least counting neighbor with already selected vertices, least external neighbor with the already neighborhood, and this Boolean dimension, that is the same as the Boolean. So we experimentally tested this approach, and the measure of there are different measures that we can compare this ordering, the Boolean upper bound, and time needed to generate the decomposition, and the time for dynamic programming using this decomposition. So how we compare? In terms of Boolean with upper bound, the greedy one, the least Boolean dimension, this outperforms the other one. But it takes too long time as it requires computation of Boolean dimension and share time. And for larger graphs, that's why we use only the other two ordering. And the ordering also outperforms the O1, and the average distance from the fixed up or down is 60% for O1, 34% for O2, and 24% for O2. And we also compare the time required as expected, the gradient is slower, and O1 is the fastest in the case. And the average distance of the fetch time, because base total running time is 12% for O1 and 300% for O2. And then we dynamic programming using vector calculation. We solve maximum independence problem using this capital decomposition. Given a graph, we get a capital decomposition. This is the underlying graph, so this will be equal to this, like this much. And we can think of that in the initially, all the vertices are in the right side, and the left side is empty. And as the algorithm proceeds, one vertex will become each step, and we will counting the residual vertices. What is that? For different maximum independent sets in the middle, it shows different neighborhoods and the size of the maximum independent set in the left. And add one vertex on left and right to left at each step and update the table accordingly. So that when the algorithm is done up to this stage, we have this neighborhood on the other side and this as the maximum independent set on the left side corresponding to this neighborhood on the right side. So what experimental results say? So we have used the previous orderings O1, O2, O3 for experiments, and apart from that we also use vertex selection on the fly, like without the pre-computed ordering. So what strategy we choose for vertex selection on the fly? The vertex being present in the most number of neighborhoods in the list, we pick that one, but this requires an extra scan of the whole list, but this strategy can be customized according to the problem being solved. So lower bound for only the branching evidence and the branching mountain. We also take the connected component and we use an ordering that has this connectivity. And when we compared it with dynamic programming approach, neither the dynamic programs nor this branching one almost contradict one another. For some graphs or for some set of graphs, branching was better, and for some graphs, dynamic programming was better. And one thing we also notice that checking for disconnectedness does not always help. For some graphs, it gives better running time when checking for disconnectedness is not there. But one thing that we also notice that dynamic programming has a amount of memory than the linear given with time, because then you have to store a long list and all the neighborhoods on one side. But the branching algorithm gives performance against other different leads, and by product we get a new maximum independent set algorithm. We write simple preprocessing rules. We use the method dynamic programming. So in the sense that we can say that Boolean list has potential to be used also in C. And we know that algorithms, when we compile, analyze, implement, and experiment them, we can give some feedback to the algorithm. So we have patterns of this that we publish later. So far we have only tried the exact computation of Boolean dimension. That we just demonstrated. That something like Boolean demonstrate or insinuate. But upper bounds on Boolean dimension can also be tried. And approximation can also help in sampling. And we have very simple, but in local struct can be explored a little bit more to see how it can help in business. And we can modify infinite independent image spatial graph classes with a good idea how it can construct a generator. And more complex reduction tests can be used. And dynamic programming for other and other problems can also be tried. And several algorithms that we tried can also be parallelized and rewrite the potential for something. So that's it.
I wish to thank the candidate for her presentation, and I ask her to remain on stage, waiting for the examination by the opponent to start. I have the honor to call upon the first opponent, Associate Professor Hans Bergen.
Thank you. Gisaka. Before I start with my questions, I would like to tell why I like your thesis and why I think it's actually very important work which has been done. And I would maybe start with I worked on myself for many years is the notion of tree-width. And what happened there is that it started really as a very theoretical concept with very highly theoretical work like the theorems of progress and receiver. And slowly people began to realize that this actually was useful also for problems that people experience in practice, real operations research problems. And I did a little work there myself with Foster where we implemented things. But tree-width and there's similar work to branch width and Higgs and block width also seen that. But all these notions like tree width and class width and branch width, they work only for sparse graphs. Basically, the number of edges in the graph can only be n times the width, or 1.5 n times the width, or something like that. So linear in the width of something like the product of the width and the number of vertices in the graph. So for sparse graphs, there are these notions. Now for dense graphs, there are notions which also somehow work like tree width, that you can solve any hard problems if this width is bounded. And the first one was introduced by Purcell, this notion of clique width. And there you see again a number of theoretical notions and theoretical results building up: clique width, NLC width, rank width, Boolean width. And what I really like about your thesis is that you actually show that this Boolean width is actually useful in practice. And I think this is important because you can, as computer scientists, you can think of a lot of theorems, but if these and theoretical algorithms, but if you don't show the world that these algorithms are actually useful, then it is just playing. What we have done is make this whole quantity work with notions of dense graph, show that they're actually good for something. That you can actually use these approaches for solving real-world problems of dense graphs. And I think that is an important contribution. What I liked about your thesis is also the methodical way you attack this problem. You did not look at one way, you actually looked at heuristics, at preprocessing, exact algorithms, the width of how you have explained that all in your talk nicely, but it's a methodical study where you look at several aspects of computing this width, and you look at all of them and got a lot of results. And then in the meantime, I would mention that these new algorithms for counting maximal independent sets is a really nice and important byproduct, which has its value on its own outside this whole notion. So in that sense, I really like your thesis, and I think it makes an important contribution to the field of this width notion. And a contribution which is unfortunately so far, I think, sparse in our field, but I think it's really nice and good that you have that. So my compliments. I like the way you read your thesis. You wrote your thesis. It's fast to read. It's well presented and great. So that's what I think what I wanted to say first. And now I have a number of questions. I have a few general questions, and then I have on a number of chapters I have some specific questions. So let me start with maybe a little bit silly question, but I hope you don't think it's too silly. But you write Boolean with a small letter b, and so lowercase b. So bool is actually named a person. So I wondered, shouldn't you write Boolean with a large b, or? Okay, thank you. So I could not find it in your thesis, but can you tell me what is something known about the complexity of designing Boolean width? Is it known to be hard or only one time, or is it still open? So, as I said in my introduction, I see two main families of width notions: the sparse graph ones, the tree width, range width, path width, and the dense graph ones, and clique width, and also with range width, Boolean width. So basically, of the latter ones, Boolean width is the only one with the systematic study of its practical computation. Do you think such a study would be a good idea for the other members of the family, or In some years ago, I had a friendly but heated discussion with young Bergen on the logarithm in the definition of Boolean width. And I was arguing at that point, and whether young Arne convinced me or not, I'm too secret here. But at that moment, I argued that it's better to stay in the area of integers, because if you add a logarithm to the definition of Boolean width, it's not an integer anymore, it's a value. So, and it's nicer to work with integers than that was at least what I was making. So I would like to hear your opinion about the logarithm. Do you have an opinion about it?
Started comparing the unions of neighborhoods, and then I have to compare it with the city that we live around. So I did some work, but as you know that these 3D upper bounds and the heat width and rank width, all these upper bounds are like similar integer and this is the SPT algorithms are true to the this parameter. So then I have to there is a balance in the SPT algorithm. Then the SPT algorithm in Bergen will be O of the cardinality of unions of neighborhoods. So actually it was to balance the SPT algorithms to have same exponential in the SPT algorithm. But yes, it's nice to work with integers.
And thank you. Let's see. I'm going to my questions on part chapter 3. One of the questions I have was you have basically a I think some of my questions here that were nicely answered by your presentation, so I'll skip those. So why 1,000? You had at some point a candidate in 1,000 seconds. Why did you choose this bound, and do you think it's sufficient?
No, it was not actually sufficient. Later on, after we were done with the paper, then we tried to extend this bound. But there was some fine balance. Like this 1,000 seconds is sometimes, for some graphs you wait for 1,000 seconds and you do see improvement, and for some graphs almost of same size, it was like in 100 seconds it was done. So we tried experimenting with that one. At some point we set up the time as a function of the number of vertices, like QT divided by 10 and 1,000 and minimum of 3. But this was like there was no consistency, so we didn't stick to that one. Like allowing time function of number of vertices. I think there should be more experiments to figure out how this improvement relates to the graph size or if there is any significance in this one. So this 1,000 seconds were really, really successful.
If somebody had even more time, would it be useful to have some scheme like simulated behavior to the local script?
I think this is actually like we just deterministically fit, but there might be some probability function that we choose it or sometimes we go little beyond the current graph and then allow it a bit more freedom then like to choose for like it might be useful for the in the long run. So like in the slopes or if you want to get rid of the local minimums or local maximums and all these things. So these values were accumulated and then this determined this thing.
Thank you very much. So my next questions are on chapter 5, the chapter on preprocessing. Well, I first have a question. You call this chapter improving I don't remember exactly. Why don't you call this chapter 2 says it, but you gave this chapter improving the computation of
We
Bergen.
actually in this chapter 3 processing for Bergen, but finally we add some improvement that we add some more experiments that how pre-processing improves the first algorithm and how this counting improves the first algorithm. So when we added this stuff at the end, we see that it makes it happen.
Okay, thank you. So, probably the next step for another reduction rule would be to reduce vertices of degree 2. Do you think there is a rule which can deal with vertices of degree 2? Okay, yeah. Okay, yeah. So, if you cannot degree slightly simpler than maybe vertices of degree 2 is if we have, suppose we have in, and I'll explain why I asked this later, but suppose I have a long path in my graph, and all the vertices on the middle of the path have degree 2.
Okay.
Yeah, so I have a long path, and only the endpoints of the path have degree more than 2. Is there, if this path is long, is there some rule that you can actually shrink this path?
You have to do something smart so that it can influence or increase the width of the path in this one. Then you can definitely
Do you know if something is known about kernelization for Bergen width?
not super far.
So my next questions are on section 6, chapter 6. So suppose I don't have a full composition at the start with the branch decomposition. Do you think there is some approach like that as you write down in chapter 6 would be possible?
The tree decomposition approach was nice because of the separator property. Like if you have a separator and then you have some vertices on this side and some vertices on the other side, and when you combine the vertex structure from these two sides, they only interact through the separator. And this will keep the moving width beyond the value of the maximum vector. But as branch decompositions are they are quantified using the edges will be underneath, and they are known as edge separators. So yes, it can be possible as well. So you have to modify the or you can map the vertices to edges or backwards transformation, and then you can transform from one decomposition to another.
I wonder, if you make this transformation, and is actually, are you spending because computing, if you someone gives you a
random experiment, I think this is undervalued in our community, and I think we should encourage more students to spend a little time at the keyboard. So I have some questions relating to your choice of data, and also how you thought some of these things might go forward in the future. So maybe let's start with questions about the graphs that you worked on. So you worked with Erdős Rainey, sparse air distribution landing spots?
The one that is landing there or craft is vertical like 80 to 100, then we try these are safer with the constant.
Right, so these are quite dense.
Quite dense. And then this one, here we have the head that 0 to 1, and the number, but it is not because with this one you only get to and then it starts taking here we have the whole thing, but for this one we have this.
And do you think that illustrating random graphs are a good representation of real-world data?
What happens when we work with random decomposition, we actually try random decomposition for real world graphs. But compared to other approaches, random decomposition for real world graphs are not very convincing. So there is a huge difference between for source graphs, random decomposition is very some far from the best one. But for real graphs, random decomposition is as good as any decomposition. So there should be some difference between the real world and the decomposition.
Can you look at any other random graph models?
No, not for source graph, because everything moves in
If you were to look at another random graph model, what might you choose?
I think we actually tried as many, quite a few random models from Alice.
Sure.
So it was Molari,
So Molloy fixes the degree distribution.
distribution. Technically, I think it's really nice. So having the distribution of my choice, then I can, like there is a big probability of visualizing the graph or getting a relation to the actual structure when you know the different distribution. Then you taking the things like how random decomposition on those models looks like.
So when you say a random decomposition, you choose random separators?
It's like random half and half of 80%. Like you have vertex view, it's like point up and left and head and tail, left and right, left and right.
So what would happen if we change the balance a little bit? 60-40.
Oh, that might be like
Do you think this would improve things?
that is really hard to say.
So in a related question, you used the program NED, so Needed, by George Carapace, and it finds these nested dissection orderings. Now, when I've used Needed in the past, it's hard to use. It's hard to get the data you want, and it has a bunch of knobs that you can turn to change things. Did you try adjusting any of the default parameters?
No, we actually not tried, but we thought of because the balance that we used was half and half. Because there might be a separator at like with 20% and 80% at on both sides. But we actually tried half balance. So because this is like what do I say? It's a bit dangerous. If you change the parameter, then it might get better for some graphs, but might be very bad for many graphs. So we actually stick with the half and half balance. But when we tried the maximum independent setting in different rounds, and then we saw that without taking kinetic components might be better than with taking components sometimes. And then we investigated the component side.
We did some experiments a few years ago where it appeared that the upper and lower bounds that we could compute on tree width specifically were very, very far apart on real-world graphs. So these greedy approaches gave us very large upper bounds, but all the lower bounds that we could compute were very, very small. And it's still open where the true answer is between these two. Do you have any feeling for whether the upper bounds you're computing are close to the truth?
I can show you one thing. This is the exact value of some random box. Exact value of some random box. And this is the value from random decomposition. So this is where we can think of it as upper bound, and this is the exact value.
But these are random upper bounds, not from one of your carefully designed heuristics.
Yes, and this actually, and I was specialized this one because this difference in this actually also not consistent. Like this is also not consistently. It's not like that the density, the upper bound and the actual one is very quite consistently also. So we have to say how this upper bound to
Do you think there are certain classes of graphs where these heuristic upper bounds probably are close to type?
I think I'm quite dense at this heuristic.
Okay, so if we choose graphs where the edge density is quite high, you think these upper bounds are close to the truth?
But partially it's a bit hard.
That's where we were working with tree width, the graphs were very strong. I'm not sure what I believe about the answer to where the true tree width falls. Okay, so I wanted to ask you a little bit about the dynamic programming on the Boolean width decomposition. So we did some experiments where we compared the amount of time it took to do the Boolean width decomposition and the dynamic programming for maximum and minimum set. And you also looked at the actual width of the decompositions you were using and used that as a quality measure. Did you find that the amount of time it took to do the dynamic programming was well correlated with the width of the decomposition that you found?
It's actually here it is, this is the limit of the dynamic algorithm, and this is the logarithm of the time squared. So it's not quite the origin, but it sounds like this. So if that is the logarithm of the time, so we can say that the time squared is due to the.
So you think it's fairly consistent with the width? Okay. Do you think something like, so Boolean width is an extremal measure, right? It's a maximum over something. Do you think something like the average?
That would be really nice actually to make it because there, in a linear decomposition, it may be that one bipartite got 40 or something, but the other ones are quite small, like 10. So then actually you somehow don't get the exponential factor overall while using this decomposition. But the decompositions that we tried actually, like in this region maybe, you don't get when almost every cut is small or close to these small numbers, then you don't get the difference. But when even one cut is quite high, like at 220 linear Boolean width, then actually this will dominate the total time, even though the other cuts are a little bit small. But the average of all these cuts, the number of cuts and the time, the average is really good to measure.
And did you measure the distribution of the cut size?
No.
Okay. So it would be interesting to look at whether.
And I'm happy to conclude that the committee has accepted both the presentation and the defense, and will thus recommend that Sadia Shamin should be awarded the degree of Philosophy Doctor at the University of Bergen. The University Board will be notified accordingly. The formal disputation has now come to an end, and the candidate may have the floor.
waiting for long for us. And my husband and my son, they are like, they always stand by me. Even when I was stressed, I was disappointed, I was happy, they are always fighting for me. So thanks to everyone. I hope I will see you somewhere. Be ready.
The entire ceremony has now come to an end, and as a tribute to the new status of the candidate, she is kindly asked to lead the procession now.